Okay, well, off on our next piece of the adventure here in Chem 1212. Kind of new at trying to make the videos without any interaction, so y'all bear with me on this. Um, to get started, remember please that you need to go back and check on your understanding from chapter 5. Now, this was back in Chem 1211. It's chapter 5 in our current textbook. So whichever one y'all used, if you did it here at Dalton last semester, you probably did use the same one. This is your enthalpy. So delta H stuff. Make sure you go back and look at your delta H stuff in chapter 5. Make sure that you understand that. If not, pause the video now and go do that and start sending me questions of what I need to give you about chapter 5 and about thermodynamics to catch you up before you try to go deeper, because we're going to build on that foundation. So there's a really neat deeper concept here. And so time, and how much have you thought about what's going on, what time is? Consider this picture of the solar system. Now, let's do a hypothetical where let's say you could see a video of the solar system happening, right? So you see the orbits. So you would see planets going round, right? Okay, so now take that hypothetical video, right? Run it backwards. What does it look like? You would see the exact same processes going backwards. And it turns out that all the physics works. Your orbital dynamics work just the same for this simple solar system mechanic going backwards as they do going forwards. So you can't, looking at the video, you can't really decide which is the real direction, forward or backwards. And the neat thing about chemistry is that we're dealing with enough pieces of things that that's no longer the case. We can see a directionality of time, and that's what's bound up in this concept of entropy that we're going to get to here. So we need to talk about the idea here of spontaneous processes. And spontaneous is probably a term that you've encountered in common usage, and we probably need to be a little more precise about it in science. A spontaneous process is one that's going to happen without a driving force. Now, later when we get into the next piece of this chapter, we're going to talk about what that driving force is all about. But for now, let's just say that things that happen without you having to apply external energy are things that are spontaneous. So this is an example here. If you take white phosphorus, like if you've ever heard of in any of the games that you might play, if you've ever heard of a white phosphorus grenade or something like that, white phosphorus is used in a lot of military applications because when exposed to oxygen, it just naturally ignites very quickly and very energetically to turn to this other compound, P2O5, which is a gas phase. The P4 is a solid. You don't have to light this off. You don't have to strike a match or anything. All you got to do is crack it open and expose it to oxygen, and this reaction happens. So that's what we mean by a spontaneous reaction. So a lot of times we'll talk about, this is where we can get a little confusing with our terminology. So back in chapter 5, remember that you're supposed to have the enthalpy stuff going in your head here. We talked about exothermic versus endothermic reactions. So you have to have that going forward here. But it is often the case, like with the phosphorus that I just talked about on the last slide, and with this reaction here, if you have hydrogen gas, oxygen gas, and then this time you do need a spark to set it off. But once you set it off, it's spontaneous from there. It reacts to form H2O gas and lots of fire, lots of energy. So it is an exothermic process, but it's not going to always be the case. So the delta H is not exactly the whole story. I mean, it's the Chem 1 story. Now you're in Chem 2. We're going to take that, of course, and we're going to make it more complicated because that's what we do, right? So looking at these reactions. So this is methane, CH4, and you can burn it in oxygen, produces CO2 and H2O. Well, delta H here is a negative value, and if you look back to chapter 5, you'll see that means it's exothermic. So this many kilojoules per mole of reaction came out. Well, that's a pretty good bit. Burning methane actually produces a lot of energy. This reaction is also spontaneous. Once you start it off, it runs. Similarly, this is we talked a lot, and we're not done talking about acid base, right? So H plus OH minus, those combine spontaneously. You don't need to spark this one off; they'll just do it. And delta H is negative. Well, cool. That so far it looks good, right? You have exothermic processes, and these two exothermic processes are also spontaneous. Now it's going to get more complicated. Now let's look at the notation I have here, H2OS. So this is a solid form of water, which you're commonly going to call ice. So if you take ice and you set it on the table, what spontaneously happens to that ice? It melts to form a liquid form of water. Now, you already know that to be the case, that if you put ice out at room temperature, it's going to spontaneously melt to become liquid. But think about the delta H involved. It must be absorbing energy in order to change from a solid to a liquid. So it's an endothermic process because the delta H is positive. But you already know it to be spontaneous. Huh. Okay, now look at this next one down here. This one may not be as intuitive to you, but if you take this solid, ammonium nitrate, and you put it in water, it spontaneously breaks up to make ammonium ions and nitrate ions. And if you do this, you will feel that the test tube or the beaker that you are dissolving this in gets cold while that salt is dissolving. Well, it does that because this is an endothermic reaction. However, it is spontaneous. So here we have the idea that you can have endothermic or exothermic reactions be spontaneous. So there must be more to the story than just the delta H thing. Okay, this slide I'm just clarifying some terminology. This slide and the next one. So spontaneous means it's just gonna happen. Now sometimes that may need an activation energy, and that's a different issue. But once you get it started, the reaction's just gonna run in that direction. But remember that most reactions are reversible. So look at this. We've got hydrogen gas and we've got oxygen gas here. Now, once you spark those off, it is a spontaneous reaction that all of the hydrogen or all of the oxygen, depending on which one is the limiting reactant, all of it is going to burn and become H2O. So this is a spontaneous reaction, this direction. But you could write this reaction the other way around and say H2O makes a balanced chemical equation with 2H2 and O2. But this we're going to call a non-spontaneous reaction. Now, when we get to the next chapter with redox and electrochemistry, we're going to talk about how we can cause this non-spontaneous reaction to happen. But we have to do something. We have to apply some energy source to cause this to happen. This one that I've labeled as non-spontaneous does not just happen in that direction. So non-spontaneous doesn't, and spontaneous does just happen. Another another important thing to talk about is this idea of labile. So it's important not to confuse it with how fast, with do not confuse spontaneity of a reaction, whether it's spontaneous or not, with how fast the reaction runs. Okay, so a substance is not necessarily a substance that will not react spontaneously. That's how we define stable. Unfortunately, we have another term that we have to use that if you just put something on the shelf, it can be kinetically stable, really means it's non-labile, this term that I started this slide with. That is just the reaction is so slow that it's just not, you can think of it in common usage as stable. It's just when we look at the very precise terms in chemistry, we don't call it stable, we call it labile. An example of this is diamond. So we talked about early on that diamond is not a stable form for carbon at Earth's surface temperature and pressure. But you don't see people's diamond rings just falling apart, and that's because it's kinetically stable. The reaction is so incredibly slow that in not only just in your lifetime, but in the lifetime of the human species, those diamond rings are not going to degrade to carbon without you applying a lot of heat to the reaction. So so they are labile, but they're not actually stable. So in this instance, we're going to talk a lot about flow of heat energy. This is going to be an important concept to internalize and keep when we're talking forward through this. So consider these two blocks. Let's say they're, I don't know, metal blocks, so metal cubes. And cube X, let's see, T sub X greater than T sub Y. Now, what does Chris probably mean talking about this? So probably means capital T temperature. All right. So block X apparently has a higher temperature than block Y. Okay. Now what happens? What happens if you take this higher temperature block X and put it into direct contact along the surface with this lower temperature block Y? So intuitively from your prior experience in life, you know that heat is going to flow from this hot to this cold material. So heat transfer is spontaneous from high temperature to low temperature. And that's going to matter. We're also going to have to talk about what temperature even means. Hopefully you got a little bit of that back in Gen Chem 1 in the calorimetry stuff. So if you've not done the calorimetry stuff or you've not looked at that in a long time, also go back and look at it. It's going to matter. And there's actually an experiment I hope that you got to do in Chem 1 with calorimetry where you actually put the little styrofoam coffee cup that you're measuring temperature as the reaction happens to try to tell delta H. Well, what you're doing is you're looking at heat flow into the water because the water is cooler than the reaction and therefore heat flows from the hot, in that case the components of the reaction, to the cold, the water. But overall, whatever heat energy is, and we got to talk about that, but whatever it is, apparently there is no net change in how much heat energy, and that's a fundamental concept of the universe, is that energy cannot be created or destroyed. Well, I guess technically I should say mass energy cannot be created or destroyed. It can only change form. But for us, we'll keep it simple because we're not going to do any Einsteinian or relativity type transformations here. So we can just say that the overall sum of energy in the system has to remain constant. So, where does this leave us? So if spontaneity is not determined by the delta H about whether it's an exothermic or an endothermic process, apparently it is not, then there must be some other factor involved. And it turns out that this other factor is this big deal called entropy. So you need to go to your textbook and start reading about this concept called entropy. And I will see you in class on Wednesday. My intent right now is to continue with where we were and calculate some more of the acid-base titration. But I hope you go ahead and watch this, and then I'll start making new videos to catch us up. And we'll go from there. All right, see you Wednesday. Bye-bye.